Hello everybody, welcome back to Bleepin' and Bloopin'. Today I want to talk about an interesting thing that I was patching up over the weekend. It's a bit of maybe an extension of a previous video where I talked about doing rectification using my Analog Select To and Compare To. Recently I've been looking into this module from Nonlinearcircuits called the Neuron. I've been really interested in this module because it's really useful in feedback circuits. It is pretty much a module that replicates some ideas from cybernetics, and I think that's pretty applicable to a lot of the more noise and feedback oriented patching that I've been doing lately. But I don't have a Neuron, and I was kind of reading through the manual and trying to decide if I really wanted it or not, or if maybe I could just patch it up on my own. And one kind of important part is the difference rectifier. That's the bottom part of the module. It's actually separate from the regular typical Neuron circuit that is the top half. This difference rectifier is actually a pretty unique thing. I actually haven't found modules from any other makers that contain it. Nonlinearcircuits actually does put this to use in several of their modules. There's the bottom two outputs of a triple sloths is actually a difference rectifier based on inputs from the previous 9 outputs. I think it's used also on a couple of other modules as well, and you can buy 1U difference rectifiers from them also. So I may end up buying one of those if it proves useful, but I wanted to just do some exploration to figure out how that difference rectifier worked, what exactly it was, and maybe see if I could try to reproduce one of my own. The way that I decided to do this was to just kind of pull it up in VCV rack, connect up a scope to the outputs, and then plug in some different data values to the inputs and kind of see what happens. So this is how it works. We'll demonstrate. So there's 4 inputs. They're labeled in plus, in minus, and in minus. And we can see I'm using this 8-verter here to generate offsets up to 10 volts. If I go into in plus, we can see the red line on the scope is the out plus, and the yellow line is the out negative. As I crank up the input, you can see I'm putting in 4.55 volts, and output 1 is showing 4.55 volts, so nothing really happening. But if I go negative, we'll see that now out plus is staying at 0, but out negative is tracking the negative values of the input. And so what we have here is half-wave rectification, much like I highlighted in that previous video. So the positives of the wave are output at out plus, and it's 0 when it's negative, and the negatives are output on out negative, and it's 0 when it's positive. So that's pretty simple. All we have here is a rectifier that sends the positive rectification out on positive and the negative rectification out on negative. But that's with just one input. What do these other 4 inputs do? So we'll connect the second one here, and we'll see it actually behaves exactly the same. We leave output 1 at 0, and we move output 2. We can see it does exactly the same thing. But if I send something into both, they become added together, and the outputs similarly rectified. So we're just seeing a mixture. We're just mixing the 2 inputs and then doing the rectification. So what about the in negatives? I'll go ahead and just hook up 3 and 4. And so we can see here, when I apply a positive voltage, we see it on the negative, And when I apply a negative voltage, we see it on the positive. So N negative is doing pretty much exactly what that minus sign would tell you. It's inverting the input on that channel. Same thing is true for the other input negative. It behaves exactly the same way. And similar to the positive ones, if we send voltage to both, we'll see them be added together. And then we can add in our positives also. So what we really have here is a 4-input mixer that inverts these two inputs. And then that whole mixed output is sent to this rectifying circuit to give us the positive rectified wave on one output and the negative rectified wave on another. It's actually pretty simple. So now that we kind of have a straightforward idea of how the difference rectifier works in the neuron, maybe we can try to build one in VCV rack. So what I have here is basically the same setup. I'm just multing this to make it easier to connect across to multiple things, and so we can more easily change the input rather than having to rewire 12 different things. And this top row is exactly what we were just looking at in isolation, where we can see the 4 inputs being sent in and then being mixed together and rectified. It's exactly what we were just looking at above. What we have here on this second row is my recreation of this circuit with some basic VCV rack modules. Here we have a rectifier, which does exactly the circuit that I described in my previous video. Takes an input, the positives of that input come out on plus half, and the negatives come out on minus half. And then I'm using this quad polarizing mixer here just to simulate this 4-channel input. So channel 1 and channel 2 are set to unity gain. Channel 3 and channel 4 are set to negative unity gain. So what will happen is inputs 1 and 2 will be summed as they are, and inputs 3 and 4 will be inverted and summed into the final mix and go here. And so we can see this behaves exactly the same. If we watch this scope and this scope, we see exactly the same results. So we've recreated the bottom half of the neuron in VCV rack, no problem. What if we were to try to recreate it in hardware using the rectification patch that I've shown off in that previous video? So that's what I have going on here. This scope, so I have the same 4 outputs patched to my Bifaco AC/DC, so I get the outputs into my hardware modular, and then I take my 2 outputs from my patch and send them back in and show it here on the scope. So we'll take a quick look at what I've done here in hardware. This is the same rectifier patch that I've gone over in a previous video using select to and compare to. I've just multiplied it by 2 so that I can get the positive rectified signal on the top and the negative rectified signal on the bottom. So just a brief reminder of how this works. We have compared to channel 1 set such that the window is all positive values. And so basically how we do that is we max out the size and then we max out the shift, and that shifts the window so that the bottom is at 0 and then everything above that is positive. It's not really any positive value because the window is not infinitely sized. And in fact, we can probably see some interesting behavior on the scope later on. But what this will do is anytime the input is in this window, which is anything above 0 within the size of the window, we will get a positive output. And so you can see here, I have the select to set in the middle, which is 0. So our signal is being completely attenuated to nothing. But when the compare to detects that it's positive and we get a positive output, we send that into unity on select. And so in this case, we will see select switch to unity from 0. And so the output here will only be the cases of when the wave that's coming in is positive. The second channel of compare to is set up in the opposite way. Again, the size is maxed out, but we're shifted all the way into the negative. So we end up with, if this is the x-axis, we end up with a window here. So anything below 0 up to the size of the window will cause a positive output on the second channel. So this select 2 is set up in the exact same fashion. It's set at 0, so by default, no value is coming out of select 2 output. But whenever the second channel of compare to detects a negative value, it will trigger this unity input on select 2, which will then output the unity value. So all negative values will come out on output 2. So that is our positive and negative rectification circuit. We get positive rectification here on this gold patch cable, which is the red line on scope 3 there. And we get the negative rectifier outputs on this silver patch cable, which is the yellow line on scope 3 there. And so how are the inputs set up? So I'm using my 3X Mia because it conveniently allows me to do pretty much exactly what I did with the quad polarizer in VCV rack. The top section of 3X Mia is set to have both channels all the way positive at unity. So the signal that is coming from VCV rack will pass through on both channels unaffected. The interesting thing here though is that you'll notice I have the top switch clicked down. And what that does is it passes the results of the top section into the middle section where they're mixed together. And then the middle section, you'll notice I have the knobs all the way counterclockwise. So this will do inversion of the inputs. So these two inputs will be inverted, and then all 4 inputs will be mixed and come out of the middle channels, plus or minus A, plus or minus B, which then becomes our signal that is sent through the rectification circuit. Results in exactly the same behavior as the quad polarizer over here on VCV rack. We can see yet again, if I take and I do an input into 1, we can see we get the exact same behavior. I'll add some to channel 2. That'll be the second gold line. Then I'll add some to channel 3, which is the inverted. So as I add, we'll see it actually decrease. That's our third channel here, the first silver line. And then the fourth channel, I'll go negative, and we'll see we'll actually increase as we invert and mix that in, and that's our second silver line. And so you can see on all 3 scopes here that we actually get the exact same behavior in all 3 scopes. So we have built a difference rectifier very much identical to the nonlinear circuits difference rectifier from the Neuron. The reason I have this whole mult thing set up is to make this part easier. I'm gonna remove my offsets and instead connect some random LFOs from the volt caudal here. And then that's moving pretty rapidly, so it's a little hard to see. So I have the scope set up to trigger. Oh, I need to turn that on. And what I'll do is I'll trigger the scope, and you can see there is a little bit of phase delay here. That's, I'm assuming, the result of the AC/DCs converting to digital to analog and then back again. In spite of that little bit of phase shift, see there's a little bit of delay on the one going into the hardware, we can see that the waveforms are identical. And we can just trigger this a few times and catch new data. We can see we're always tracking identically. And so that's some pretty, I don't know, I find that to be pretty interesting and pretty cool. It's a really neat circuit. I think it's gonna have some interesting usages in feedback patches. First thing I'm gonna do is actually use it to try to recreate a module from Zlob that was kind of inspired by the Benjamin, and that'll probably be my next video, showing you all that patch where I'm trying to rebuild a different module using this patch that I built. I do want to show this one interesting thing where we can get some pretty wild behavior. I'm going to add an LFO here and put that in place. This is one difference of this circuit to the actual Neuron's difference rectifier, and also a difference from the VCV rack one that I built. I'm going to put in another LFO here, and the reason I'm choosing to use this one is because the output values go higher than the caudal, so just replace that. And you can see the difference I'm talking about right here. What happens is in the Neuron and VCV rack, once we hit a peak value, we just get a flat cutoff at that peak. So basically like a hard clipping distortion. The same thing happens here in our rebuilt version, though I think our value is higher and it's going off screen. I'm just sliding it down so we can actually see the whole waveform, but you can see it doesn't get hard clipped like the Neuron circuit does. But on the hardware version, when we hit that hard clipping, we get a big nonlinearity and drop back down to 0. And the reason for that is because if we have our window and our value goes above it, the way compare to works is when you're outside the window on either side, it returns false. So as we go above, it will also trigger a false here and cause us to go to 0. So it's a difference. If you keep your levels within the range of the compare to, you won't run into this at all. But considering we're creating chaos circuits and we're also primarily going to be using this in a cybernetics feedback types of things, the nonlinearity here will actually kind of add to that. We could use the difference rectifier as our transfer function for a Neuron type circuit, which is some details that we'll probably go over in another future cybernetics based video. So I hope you found this interesting. I'm pretty excited to have another use of some of my favorite modules here, select to and compare to. I feel like I use these modules like in every single patch to do something interesting. And every time I try to think about, oh, could I build this other behavior that I want, I always end up using these two. So highly recommended. I think you'll love them as much as I do if you love patch programming as much as I do. Well, thanks a lot, and we'll see you on the next one.